All right, so for our next colligative property, let's think through things a little bit. Remember before we defined boiling, and we said that boiling doesn't necessarily happen at a specific temperature. When boiling really occurs is when the vapor pressure of your solution is equal to the atmospheric pressure. Remember, your solution's kind of trying to push up, the atmosphere is trying to push it down. And so when the vapor pressure increases to the point that it matches the atmospheric pressure, it can go ahead and boil. But as we've seen, solutions have a lowered vapor pressure. They have a lower vapor pressure than normal. And so since their vapor pressure is lower, in order to match our atmospheric pressure, we must get even hotter. And so the vapor pressure of solutions is lower, so their boiling point is increased. And so this colligative property is known as boiling point elevation, because your boiling point is increased. And so it gets this equation of delta TB, the change in the boiling point, is equal to the molal of the solution times KB, which is just a constant. Again, this TB here is change in boiling point. This is molal or molality. Remember, that's moles of A over kilograms solvent only. And then KB here is just a constant. And so it depends on which different liquid you're taking a look at. So let's take a look at some of these numbers. So here on the left, we have just some different solvents you can take a look at. Next up, we have their normal boiling points at 1 atmosphere, right? So at normal pressures. So you can see water boils at 100 degrees Celsius. And then we have a KB value. So this is how much our boiling point is going to increase per molal of solute that we have. And so one question that I could ask you, something like this, is what's the boiling point of a 0.33 molal solution of benzene with the non-volatile solute? So for all of these kind of colligative properties, these solutes, what we're really talking about is non-volatile solutes. If you try to insert some volatile solutes, it gets a bit more complicated. And so we'll use this equation that we just learned about, and that's our change in boiling point is equal to the molal times the KB. And so this is a pretty straightforward problem, right? Molal we're given as 0.33. Our KB, remember here we're talking about benzene, so we need to find benzene on our table. There's benzene, and then there's the KB of 2.53 degrees Celsius per molal. So this delta TB with then the 0.33 molal times this 2.53 degrees Celsius per molal. You'll see that the molals will cancel out, and so we'll be left with degrees Celsius. And so your delta TB here is 0.835 degrees Celsius. And so that was all very simple and straightforward, but this is something that trips a lot of students up, and it's a little bit ticky-tacky, but it is what it is. So we're asking for the boiling point of benzene, right? And so did we calculate the boiling point here? No, we did not calculate the boiling point. We calculated the change in the boiling point, not the actual boiling point, right? So this is change in boiling point, right? Not the boiling point. It wouldn't make sense for this to boil at 0.835 degrees Celsius when the pure form of benzene boils at 80.1 degrees Celsius, right? That's a huge change and in the wrong direction, right? So remember, this is change in boiling point. So if we really want to find our new boiling point, we have to take our boiling point of our pure stuff and then add to that our change, right? So that'll get us where we want to go. So we'll plug in this 80.1 for the pure stuff, and then this 0.835 in this change. The reason we do addition is because it's boiling point elevation, right? So this number needs to increase, right? You'll always have a bigger number at the end than when you started, right? So 80.1 degrees Celsius plus 0.835 degrees Celsius will get 80.9 degrees Celsius. So just make sure you're actually answering the question, finding the new boiling point and not just the change in boiling point.